to another problem session for the MCAT JEE prep. So we are going to today continue from the previous day about momentum, in particular total momentum. So this total momentum means, say if you have a whole bunch of things there, then total momentum is a sum of the momentum of all of this. Maybe this guy is going this way, P1, maybe this guy goes this way, P2, this guy is going this way, P3. So the total would be P1 plus P2 plus P3, and this is very importantly vector. So this is a vector sum. So if you don't know what that meant, you need to go back and review your vector chapter. Okay. Okay, so collision basically is a particular type of phenomena where some object is moving along. So I have a frame here. I'm observing this thing moving along, and it runs into something. So that process is called collision. So thinking about this guy, say this is V at 0. Say this is M2 and this is M1, and just before the collision, this guy is just before the collision, it's going that way. So it's going to come and hit, and there will be forces between M1. So this is just before. So there's a force. This applies we say before and during. So this is just before. So if the picture during looks like this, during the collision, this part and this part, they get a little deformed. So that part, this is during, and so this you can think of, model that as a spring for M1 and a spring for M2. So they're kind of compressed. This guy's compressed and this guy's compressed. So this happened. It used to be before, used to be like this. So this is M1 and M2 before, and from this situation it went to this situation at that place. Okay, so this is during. So it's still the you might say then it comes to rest. So halfway, so the momentarily comes to rest. It's like a spring got fully compressed, so this is still during. So over here this is the force on 2 by 1. So this is on 2 by 1. And if you look at it, this spring is pushing outward, so this is going to apply a force that way on this guy. Okay, so this is going to apply, and this guy is applying a force that way. So this is force on 2 by 1, and this is force on 1 by 2. So there will be a force on the other guy, this guy, force on 1 by 2. Okay, during so this is at rest, and then the process is start to unwind, and this is still now it's got a force on 1 by 2. We'll use the same color pen for this guy and for this. So this is it's winding, unwinding. It was relaxed, it's going to go to relax, so it's going to push out. So push out on 1 by 2. So these are all and now this is after collision, the moment after collision. So this is the after, and they're not touching each other, no forces. Okay, so that's so this whole entire duration, if you look at it, if I look at these as one system, combined system, then forces are all, look at this combined system, this all internal forces, those forces are internal, forces are internal. So in a combined system, the forces this way are F on 1 by 2, F on 2 by 1. These forces are internal. This before it's just moving, there's no forces. So this is going with the V1, let's call it, and no forces. So no forces, no forces. Over here, all internal forces. We already established that all you got is internal forces, then momentum will be conserved. That will means combined momentum will be conserved. So if I look at M1 V1 plus M2 V2, this combination is combined. If you look at before, must be equal to same combination after. So whatever it is after. This was before, we had two particle system. Now in this collision after this also 2, so it's going to be 2 of this over here. So the upshot is P before, and this will be total, will be P total after. But people get confused what's internal, what's not internal, and they so over here, look at this. If I think of this as my system, then right now no force. So let's look at same problem. This is M2, and so this is M1, and this is coming, and now we have M2 as pressing, and then this is M1. Now I'm going to say this is my system, M2 is my system. Then the force from M1, so this is force on 2 by 1, okay? So on this guy. Now this is now external force. External to M2. Similarly, if you look at that M1, the opposite force from M2, so this will be F on 1 by 2, these guys are equal to each other, right? These forces are equal but opposite direction. So if I look at this as my system, this is external to it. So this force is external to M1. So if this is the case, then momentum of M1 is not conserved. M1 will change or will not be conserved. In collision. Okay, and instead it will be P1 after minus P1 before will be this impulse during. So you got to fight this impulse, and the impulse is that force, external force dt, right? So you have to do this integral or area under the curve to get that, right? So same was going to happen over here. You got to look at this as an external force, and its momentum will change. So momentum of pieces were changing. So over here, look at equation like P1 plus P2. So nothing but just the two objects remain the same, will be equals to P1, say prime, for afterwards. So if this is the after, this guy's after, and this is the before. So you can say that P1 will change certain amount and P2 will change certain amount. So they're not necessarily zero. P1 will change by this amount, and P2 will change P1 prime minus P2. So P is going to be P2 minus P2 prime. So this is the change in P1, and this is the opposite of the change in P2, after minus before. So this is opposite change in P2. So delta means change. So this is how it's going to work, right? So let's do a example in which this guy comes in. This is a maybe this is 10 kilogram, and this is 2 kilogram, and this is going at 3 meter per second. So this is before situation before, and this is v equal to 0. This is before, and then after situation. We're going to do a whole bunch of examples like this, okay? So this is 10 kilogram, and this is 2 kilogram. I'll stop writing. So after they stuck, and they move together. Maybe, let's see. So because net momentum is that direction, P total in that direction is gonna, P total here will be in the same direction as that. So this will also be in the same direction. P total, so this P total has to be equal to this P total. So it's gonna be vector in the same direction. So we just take this guy's velocity in that direction is V. Both of them will, and this will also V. So both of them going together here. So you have a 6, if this is x-axis, then this is also going to be x-axis. So P total x, just looking at that, this is 6. 2 times 3 is 6. 2 times 3 plus 0. and this one is going to be 2 times v plus 10 times v is 12v. So now this will be equal to each other, so the v will be just 6 over 12 equals to half meter per second. So thus you can figure out the v for in this situation. Suppose we have the same initial situation, 10 kilogram and 2 kilogram, and this thing is going 3 meter per second. So this is same as before, but what happened is this guy start to move at 1/10. See, it started to move. It hit so hard. 2 kilogram hit so hard that it start to move itself. Start to move 1 meter per second. So this is 10 kilogram. That way. So what will be this guy do? Okay. Well, it's going to be, of course, this is the direction. So this is going to be direction from P total. So over here, regardless of what happens, that will be the P total. So we just look at x-axis that way. Same thing at P total x. So this again same, 2 times 3 plus 10 times 0. And this we don't know what it is, so we just call this guy this way. It's because of this x-axis. So it's going to be just v sub x. So we just said 2 times v sub x. If this other way, the v sub x will be negative. Plus this one is 10 times 1. So now this must be equal to that. This is the P total x after, and this is before. So equate that and solve this. So Vx is going to be 6 minus 10 over 2 equals minus 4 over 2 is minus 2 meter per second. Now we got a minus 2, so V is minus 2 I hat because the x direction. So this tells me this, you can say 2 is magnitude minus I hat is direction, and this that means it bounced back. That's the answer. V is not that way, but V is that way. I just took it, I didn't know, so I just take it same direction as that for doing the calculation, so I can use the V sub x. So if you write over here this way, you're writing V, you don't know what this is, plus or minus, you're writing like that. And so this, if the positive then that way, negative then the opposite direction. So this is a little bit more complicated. Let's do carry on the same thing. Another example. So I have a 2 kilogram is going at 3 meter per second and is just about to hit 10 kilogram box. So this is the before, same thing. Now I am going to imagine that this guy totally comes to rest and this guy splinters, and in a maybe 4 kilogram and goes straight up like flying that way. Maybe it goes 1 meter per second that way, and then another piece which is 2 kilogram and it goes flying 3 meter per second that way, and so another 4 kilogram. What will be this guy go? What will be the V of this guy? Well, this is the after. This is a way kaboom. But we know this is collision, so momentum will become, we know P total here must be equal to the P total here. So this entire system we're looking at. Okay, so but here this could be in any direction. This is going, so we will say, let's call this X direction. So we keep the same direction X, and let's call it Y direction. So this is the X and Y directions, and this one is in the Y direction, and this one happens to go in the X direction in this problem, but doesn't have to. It just, this is the way it's given to us, and this will just give a vector. We don't know what it's going to be. It's going to be Vx I hat plus Vy j hat, and from there we're going to figure out what happened to this guy. Okay, so we have a P total X and P total Y, two situations. They're going to be P total X here and P total Y. So we are going to have to equate this with that. So this one is just a 2 times 3 plus 10 times 0 is 6, and 0 plus 0 equals to 0. This side. On this side, this becomes 0. This guy has no X. This guy has all X. 3 times 2. This guy is 2 kilogram times 3, first side, and this 4 kilogram times Vx. So that has to be equal to that. So that will so give me Vx. This guy again is 0. This guy is all Vy. So 4 times 1, and this guy is 0. 2 times 0, and this is 4 times Vy. And so must equate to that. So separately I equated. Excuse me. So 6 equals to 6 plus 4 Vx. Oh, that this is Vx is 0. I set it up like that. Excuse me. And this 0 equals to 4 plus 4 Vy. Then Vy equals to minus 1. So this tells me these guys come straight flying down. And I set up the number so that it will work out, because I know the original was going to be 6, and I gave this guy 6. This satisfies the momentum conservation. This is same as that. Then these guys have to kill, the momentums have to kill each other. So this is, so if I had this guy randomly go there, it will go in random other direction in this problem. Okay, so upshot it is you can do even two-dimensional problems like this by just setting it up so that you have X conserved separately than the Y. Okay, now let's go back, and another type of problem people can ask here is, all right, so what happened here during the collision? Can I figure out anything about the forces that happened in the collision? Yes, if you know between before and after, say delta t is 0.2 seconds, 200 milliseconds, suppose, then you know how much momentum have changed. So now we're going to look at one of these guys. Don't need to look at both of them. Say look at this guy. It says what is its change in momentum. So we look at this guy before, and delta t was with 0.2 second. So this guy v was 0, and this turned out to be over here half a meter per second, and this is 10 kilogram. So in this situation, you know, change in momentum is along the x-axis. So we have a px. If this is t, then this is t plus delta t. Px, let's call t equal to 0 before and t equals to delta t after. Px at delta t minus px at 0. So that's the change in x equals to impulse x. So this was 10 times half minus 0, jx equals to, and it took this long. We don't know what the force is, so we can assume the force looks like this. Some average force. Assume that 0 to delta t is like that. So it will be, jx will be some average force times delta t. So we don't know if it was like this, like that. What kind of force diagram was there? We don't know that, okay? So in the absence of that, we can only talk about average force. So the average force that this object applied on that object can be obtained from here. So this is F average times 0.2, and this is, so F average will be, this is 5 and this is 0.2, so this will be 25, 50 over 2 is 25, yeah. So it's going to be 25 Newton in this problem. Now you can do the same thing here. So find average force if during collision is, say, 0.2 seconds. This is not bad time for collision. Over here, you say, hey, what kind of average force was applied? Then you'll have to think of this change in momentum, this versus that system, or you'd want to think of this system versus this system. So that's easier to work out, right? So in that situation, you have a 2 kilogram, 3 meter per second. Let's see, delta t is again 0.2 seconds, 0.3 seconds. 2 kilogram going this way, but it comes to rest. So if you look at this x direction, this minus this momentum will be, delta px will be minus 6 kilogram meter per second, and we're going to equate this with average x times delta t. So, and this is the average that this box applied on this 2 kilogram, and the delta t is 0.2 seconds. So clearly you can say if average x is minus here, because the positive axis is that way, so the force is opposite, which makes sense. The ball got stopped, was moving, got stopped. So this is minus 6 over 0.2 is, so this is 60 over 2 is minus 30 Newton. So this is sometimes asked, where what kind of forces can we figure that out? Yeah, with some assumptions we can figure that out. All right. So main assumptions is assumptions of time, but we can't really figure out the detail of the forces between the collision without making further assumption, right? So we assume, okay, there's some kind of average force we don't know the profile of the force, whether force went up like this or force uh, just straight up, stayed up and came down. We don't know, but we just assume there's some average force for getting some rough idea about what might have happened, which is kind of crazy, right? Because suppose we just found out change in momentum was minus 6 kilogram meter per second, but the force so is still 0.1 second and 0.1 second if this is t. Suppose the force was kind of like, it was very significant only in this, and this was, it was significant only in 0.0102 second. It wasn't significant, so this was went up and straight up like this. It was more like this. So what would this force be? Well, so this will be that force, maybe the force x components, okay? So the F0, and so let's call it all absolute, just magnitude, forget the directions. So 6 will be times 0.02, not 0.2, because this is close to 0. So the area would be more here. So this time it will be 300 Newton. So we went from 30 Newton to 300 Newton just by looking at the detail. So the detail of what the force looks like can be different than this average force. And I always found these questions about average force during a collision totally underestimates, because when it's touching initially there's not that much force, but as they push into each other, suddenly the force kind of shoots up. Okay. So and that explains why sometimes when things hit they break, because the force gets so great that the force per unit area, the so-called stress, becomes bigger than what the body can actually handle. So it's the internal stress that's what leads to the breakup of things. Okay, we are going to do some energy things now in the next videos, and can combine the energy considerations and momentum considerations into elastic collisions and inelastic collisions. All right, so we'll see you in a video. Bye.